go to other planets, this geometrical shapes will not help us, circle or ellipse. In that case, we need to make use of parabola or hyperbola. Now, parabola means the eccentricity is 1. Hyperbola means the eccentricity is greater than or equal to 1. Now, if you want to go to other planets, what should be the escape velocity? We call it as escape velocity. Now, you gave the correct value, 11.2. Now, can you reduce it from this particular equation? This is what it gives, e square. From that, we have that velocity, v standing for the velocity. Is it possible to reduce 11.2 kilometers per second from this equation? Mu is a constant. It is related to m into g, I think. But I can give you the value for that. It's a constant. Now, as I said, e square is, e is greater than or equal to 1. That says e square is also greater than or equal to 1. Now, in that case, can you get rid of the first term? E square should be greater than or equal to 1. That means the second term should be greater than or equal to 0. Greater than or equal to 0. The second term. Because the old term we want to be greater than or equal to 1. So it is obvious the second term we want to be greater than or equal to 0. Now, if the second term you are talking about greater than or equal to 0, the first term is r0, which we actually call it as the radius as far as the Earth is concerned. Now, that cannot be negative. No. Now, v square cannot be negative. Divided by mu square, that also cannot be negative. In that case, whatever is given in that bracket should be greater than or equal to 0. So now we came to the situation where r0, that term in the bracket, r0 into v0 square minus 2 mu, this should be greater than or equal to 0. Now that gives us the solution. V is equal to, it was v square. So when you take v, it is square root of 2 mu. Pardon? No, I took a because the radius of the Earth. Radius of the Earth. R0 is the general case. But when I talk about the Earth, I take a as the radius of the Earth. Now, mu stands for g multiplied by a square. So that solution becomes v is equal to square root of 2ga. Now you do that calculation, g you take it in CGS or any system, and the radius of the Earth is also considered. This value is equal to exactly 11.2 kilometers per second. Now you see that equation may look a bit bigger, but you can easily reduce the actual solution from those equations. Okay. Now, coming to the developments, the new developments in mathematics is, I suppose you might be familiar with this picture. Anyone? No? This picture is known as Mandelbrot set. It is related to a term known as fractals. Fractals. Have you seen the movie of Jurassic Park? Yes. Now, in the beginning, there is a scene where all those people are taken by a helicopter to a particular island. Now, when they go to that island, then lands, have you noticed the surroundings? Anything special about it? There is a waterfall and greenery all around. Now, they are not actual nature. They are all created using this particular term known as fractals. That scenery given, it even looks better than the actual nature. But it is created using the fractals, not the actual one. Now, fractals came because when Mandelbrot was dealing with dynamical systems, he came across many pictures which are completely broken. Now, in the usual geometry, when we talk about, you talk about circle, we talk about straight lines, we talk about triangles. But are there any such things in this real world? Can you show me something which is exactly a circle? A straight line? No, there is no such thing which, if you look at the moon from here, of course it may look like a circle. But you know, when you go nearby, you see that it's not actually a circle. So Mandelbrot came to the same situation. He had things completely broken which cannot be represented by the usual geometry. So he started introducing a new geometry which he called as the fractal geometry. Now fractal, that word is from fractus, Latin word fractus, which means completely broken. Fractus. And from that he derived the word fractal. And this graph is the graph of the function f of z is equal to z square. I'm not saying f of x is equal to x square. It is f of z is equal to z square. What is the difference between that? F of x is equal to x square and f of z is equal to z square. Now 12th standard students are there, right? I think you should know. What's your name? Apurva. Okay, Apurva.
Is that a complex number?
Yeah, right. It represents a complex number. F of z is equal to z square. X usually, x and y, we use it for the real numbers. But if you represent it using z, it means it is the complex number. So f of z is equal to z square. You draw the graph of it, it will be something like this. Now, graph in the sense, you give a value of z, obtain z square, that z square again take it as z. So repeat the same procedure again and again. I repeat, f of z is z square. You give a value to z, so you get z square. That z square is again taken as z. And repeat it. It's a kind of iteration. But after certain iteration, if it does not escape this unit circle, for example, you take the value of 0.5. This is in the real number, 0.5. You multiply with 0.5, what happens? 0.25. Again multiply with 0.5. 0.125. 0.125, then 0.625. Sorry, 0, okay. So you see, you go on multiplying it, it comes nearer and near to 0. Now you take the value 1. Do the same calculation. What happens? It will remain as 1. Now you take more than 1, what happens? It explodes, it goes out. Now, so that means between 1 and minus 1, any value you take, it will stay within that particular circle. Now, it is the same with the complex numbers also. So, those points which does not escape, you plot it. So, you get the picture, something like this. Now, there are certain important properties as far as the fractals are concerned. The one property is, any part of it you enlarge, any part of it. For example, you see that needle shape going to the left side, only that part you enlarge, that will exactly look like the first picture. There is an important property of the fractal, which we call it as the self-similarity. What happens is that small part you enlarge, it will exactly look like the bigger picture. Now this property is used in image processing. That is, when satellite takes the photos, those photos will have to be stored, isn't it? So they need memory for that. So instead of storing all such photos, what they do is, they select a certain area which exactly look like the complete picture. And they need to store only that small area in the memory, because that will exactly look like the bigger picture. So they don't need to store all that picture. So that property is used in the satellite for the image processing. Now other properties, we talk about dimension. Can you give me one example for one-dimensional quantity? Point, it has a dimension. Line. Plane. Plane, it is 2 dimension. Now 3 dimension. Space can be considered as 3 dimension. Have you ever thought of something of dimension 0.5? Why not? 1.5. There are things existing in nature of such dimension. You say a line is of 1 dimension, a plane is of 2 dimension. Now there is nothing in between them. So you can have dimension between 1 and 2. Similarly, you find derivative dy by dx. Now second derivative, how do we denote? d2y by dx2. Now instead of 2, why it can be 1.5? Such derivatives can be thought about. It will bring results for sure. Okay. Now this is that picture I was talking about. You enlarge the smaller part of it and it will exactly look like the bigger picture. These are certain factors. Now we'll go back to the non-Euclidean part. What is the sum of the angles of a triangle? 180. Now, can you see that picture? What is the difference in that? Now, there are 2 angles with 90 degrees. Now, the third angle is 50. So, what is the sum? 230. So, it is not 180, it is 230. This happened because we are dealing with the non-Euclidean geometry. Now this another case is given there. You can see that it is in the Euclidean geometry where the sum will be equal to 180. But that is not the same case with the surface of the earth. If you consider, it is not going to be the same. Now the non-Euclidean geometry originated because Euclid gave us in his Elements, the book Elements, he gave us 5 postulates. It is on line and triangle and right angle triangle, all those things. He gave 5 postulates. In that 5th one was very interesting. Now somebody told about it, 5th one. Yeah. Can you just repeat that postulate? 5th one.
2 lines, if they are not parallel, they must be intersect.
Sit down. If 2 lines are not parallel, then they must be intersecting somewhere. That's what that 5th postulate says. Now one priest, his name was Sacheri, Girolamo Sacheri. What he did was, suppose it doesn't intersect. Suppose these lines do not intersect. And usually what happens, we know something is true and we assume that that is not true, then what we should commit? Contradiction. Usually we should get a contradiction. But when he tried that, he did not get a contradiction. In fact, he derived many theorems related to non-Euclidean geometry. Now this is the geometry used by Einstein to obtain the theory of relativity. This is non-Euclidean geometry. The main difference between the geometry and non-Euclidean geometry is the property between any 2 points in Euclidean geometry is a straight line, but as far as that of the non-Euclidean geometry is concerned, it may not be a straight line. It can be curved. That's the main difference between the Euclidean and the non-Euclidean geometry.